All right, so welcome back, everybody. Excuse me. So this is the second week of the classes. We're still doing remote. So hopefully everybody is healthy and following the protocols for UCLA. So before we get started, actually, we have Tom King from UCLA's Center for Blood Donation, if I said it correctly. So he accepted our invitation to give us a very short presentation on blood donation. So I won't give you more further this introduction. So please, Tom, go ahead.
Hey, thanks so much.
You're being recorded, so just if I.
Oh, okay, yeah, great. So yeah, my name is Tom King, and I work specifically in the Ackerman Blood and Platelet Center, so right on campus. And we're the largest hospital-based donation center in the country, which means that all the blood products that we collect stay at our hospital. So Ronald Reagan, the Children's Hospital, or UCLA Santa Monica. Generally, we collect about 80% of the blood that our patients need, and we have to acquire that blood from another source, like the Red Cross. But with the onset of COVID, and this is national, you may have heard about it, that it's really decreased. We collect now about 50% of what our patients need. In fact, if y'all want to read, there's a story today in the Daily Bruin about our need for blood, especially around transplants. We did a drive last week to raise awareness about liver transplants because they require the most number of units of blood. And there's a story in there of somebody whose father wanted to get, he waited 2 years to get his organ transplant, and then we couldn't give it to him because we just didn't have enough blood. So please, 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 if you're here or wherever you are, donate. If you've never done it, it's pretty simple. Your professor can tell you so, as he's a regular donor. Takes about 45 minutes by the time you fill out paperwork, answer some questions. The actual draw time is usually about 6 to 10 minutes. We like to say that it's a pretty painless way to directly save someone's life. And there's a lot of lives to be saved. We do have we have little incentives like gift cards, movie tickets, sometimes t-shirts to kind of help maybe draw you in as well. People have questions about regulations about donating. We encourage you to go on our website and look at our self-screening guide because a lot of FDA regulations changed with the onset of COVID. So people that were ineligible maybe for a long period of time may be eligible now. I'll put my information in the chat. So if y'all have any questions, I'd be, happy to answer them. And, we're taking all really obviously very safe protocols here in regard to COVID, but it is essential if people can to please come in and see us. So I'll, or when you come back, if you're not local right now, come on in and yeah, so thank you so much. Thanks for the opportunity. I'm just trying to get the word out as best we can.
And then can you also talk about the appointments? Because I thought did you mention that?
Oh, no, I didn't.
Yeah.
So we, right now we're open 9 a.m. to 3:40. Usually it's 11 a.m. to 5:40, but with Ackerman building being closed. You can email me. I'm happy to set you up with an appointment or on our website. It's pretty easy to do as well. I could also email you a QR code that maybe you could send out to people, and then it's like
of course, yeah.
Okay,
yeah,
so I'll send the QR code.
I think you can also call, if I remember. You can call.
Yep. So I will. But yeah, any questions you have with setting appointments, you can feel free to email me. But I'll also send you that QR code.
Excellent. Thank you.
Okay. All right.
So is there any questions for Tom? Anybody? So yeah, as I said, the process is very easy and very convenient, and it's very close to most. It's the center of campus. You just call, get an appointment, go there. Small paperwork. There are snacks actually. You can also enjoy.
I always forget about this.
There are plenty of snacks that you can use before and after, which is nice. And then, it's very quick. I'm incredibly busy, but I always find the time to go and do the donation. I also have a t-shirt. Today I'm in my home, so my t-shirt is actually in my office. I would have wear it if I were in my office. But yeah, you get sometimes you get the t-shirt or, other goodies. Like I have, I think, Starbucks, gift card. You can choose different things. But of course, the bigger and most important goal is, that's doing something that is very, very important for many people, right? So please, everybody, I encourage you to do it. And hopefully we are back in person soon. I think most of you are already somewhere near the campus, so you definitely. I think the Wall Center is open right now.
Mhm.
Right now? Okay,
Yeah.
So you guys can just go there whenever you can. All right. Okay.
All right.
Any final question from Tom? Awesome. Okay. Thank you so much.
Oh my
Have a
gosh,
great day.
thank you. All right. I'll send you that QR code.
Yeah. I'll post it to the website. All right. Thank you.
Thanks. Ciao. Have a good class.
Bye. Yep. Bye. Okay. So back into class. Let me share my screen. All right. Cool. So today we want to talk about privacy-preserving computation. We also want to, continue a little bit of what we discussed last time about, privacy. And then somewhere in the middle of the class, I'm also talking a little bit about paper presentation and stuff like that. So if you have questions about those kind of things, sit tight. We're going to talk about those as well. All right. Okay, so last time we talked about security and privacy in machine learning, right? So security and privacy, the main two things that we discussed. We basically say that, the issue is coming from the fact that, an adversary wants to either make an impact on the system and make the outcome, different than what it's supposed to do. And then we mainly say that this is like a security issue. We talked about multiple different techniques that it can be used. Generally, the two main things is poisonings that happens during the training and evasions that actually happens during the inference, different techniques, different defenses, etc., etc. There were some discussions offline on campus wire as well about this, which was really nice. I also encourage you to be more active in discussions in campus wire. So ask questions, answer each other's questions, and so on and so forth. If you, again, find something interesting, you can also post it there. If there's a paper that you think worth reading, post it there, and all those sort of things, right? Then in the second half of class last week, we talked about the issue of the privacy. And then we said that basically the issue of privacy coming from the data, right? So basically data, we want to, steal data, which could be either input data or could be model and the model structure itself, or it could be the weights of the model. And so, yeah, as I said, talk about ML privacy, we talked about. And then we mainly say that the issue of the privacy is rising mainly because of this notion of machine learning as a service, which essentially the way it works is that there is some model stored somewhere in the cloud, and people are basically through some APIs and through the internet can access this the specific network and get their data labeled or any sort of machine learning that can be used, classification or any other type of machine learning application that can be used, right? And this is kind of like a win-win situation because smaller businesses or smaller users does not need to maintain and train large machines and systems. What they can do is just basically pay a small amount of money in order to use the systems. And another thing is that, the data, collection of data that's maybe some companies or some entities only have access to can be also more democratized, can be access to a larger group of people and so on. So there are lots of benefits for machine learning as a service. And in this settings, there are essentially three different, players. The server obviously is the one that is, providing the APIs and do the inference. The users are the ones that actually use the system. And of course, there's this notion of participants or data owners, or those that are actually provide the data for the training. We also said that, the participants and the server could be the same entity or could be different. It could be multiple participants in the same server and so on and so forth. All right. So this is the general settings of machine learning as a service, sorry. And we said that essentially under this setup, there will be two potential attack surfaces. One could be that the server is actually the malicious player, which in that case, the goal is actually stealing this confidential data that is the input data. An example would be, for example, a clinic which has some sort of patient data that are sensitive, and the clinic wants to use machine learning as a service in order to label this data, for example, to diagnose specific disease or an X-ray and so on and so forth. Of course, since this is a sensitive information, the server can steal this information. So that's a vulnerability and challenge that we're facing. On the opposite side, the user could be malicious as well. And in this case, the goal is actually either stealing the model here. And we said that since the model usually is considered IP, the user can steal that. Or another thing that the user can steal is the training data that used to train this model. So that's another thing that the user can steal. All right. So that's just the some quick recap of what we just said, and let's now talk about this problem. Any questions so far? Okay. So we said that the user, what the user can steal is the model weights, the training data, and some sensitive attributes of data. So it doesn't need to steal or recover the entire training data or specific record, but it can actually, just only recover some sensitive attributes of that data. So for example, how many people are a certain age in this training data set, or what is the specific feature of each of these people that participated in this training data set, and so on and so forth. All right. So there could be multiple different scenarios where the attacker would be interested in. We talked about 3 different attacks. So last time we only had a chance to talk about one of them, which was the model extraction. So quickly, reviewing what the model extraction was. So the idea in model extraction was the user wants to extract the model stored in the cloud. The simple thing that the user can extract is the structure, but usually what happens is that the user is more interested in the weights, the actual values that's being used in the model as well. And then the way that the attacker gonna create this attacks would be basically creating some sort of this would be the main model that is being interacted and sits in the machine learning as a service platform. What the attacker will do is some sort of this shadow model that will create that's going to be, hopefully, if it does it good enough, it would be very similar based off some metrics. So the metrics could be different. So the measure of similarity could be different depending on our definition. But at some point would be very similar to this machine learning as a service model. So at that point, you can just basically discard this model and then just use this model. And this way, no longer this inputs and outputs is needed. So it could be, financial benefits. It could be, technical benefits. There could be many different things that the attacker is motivated to do. All right. So how does this shadow model is actually being trained? So usually it happens with so it's basically a machine learning problem for itself, right? So we have a set of inputs and outputs. So these inputs are created by the adversary. The actual model going to create the output labels, but this output labels is also available to the adversary. The adversary going to use this outputs and inputs to train the shadow model, get the output of the shadow model. Get the output of the shadow model. And usually we said that there's going to be some sort of algorithm here that the attacker is going to develop, make some decision based off these outputs. And based off that, it's going to recreate a new set of inputs. So this is like an iterative process. It goes back and forth iteratively until the shadow model reaches to a certain level of, accuracy. All right. So that's the main idea of model extraction. There will be some papers next week that we're going to talk about different types of model extractions. There is a question, Shreis?
Yeah, Professor, are we assuming that the shadow network would at least know what the architecture of the model is?
We may or may not, right? So again, depends on how do we want to define the similarity between the two. Maybe the only thing that we care about is that the accuracy of the shadow model is close to the accuracy of the original model. In that case, yes, of course, if the structures are similar to each other, the chances that we can reach to that accuracy is higher, but necessarily doesn't need to, right? So the only thing that we care about is this is a black box, and what we want to do is replicate the type of behavior that black box has. Does that make sense?
Okay, thank you.
Another question, Jinhan?
Yeah, Professor, I have a question regarding the question related to how to estimate the complexity of the shadow model. Since, let's say, for example, there is a single classification of image problem, and for this classification problem, the global or local optimal can be reached by different types of model. Some of them maybe follows the structure of like the transformer, and some of maybe just the convolution and fully contact layer combination. So is there any systematical way or any solution to estimate the complexity and the structure of the shadow model in a greater extent?
So that's a great question. So I mean, obviously these are the main challenges in model extraction. And again, if you look deeper into the state of the art, you will see that actually these are the problems that are being addressed. One thing that can be used is some sort of what we call domain knowledge, right? So for example, let's say that, the shadow model that needs to be replicated is, for example, for vision applications. And what happens is that nowadays we know kind of like, but for the type of application that needs to be done, roughly how the structure of network will look like. Obviously, we don't know the exact layers, the number of layers and so on, but we roughly know what would be the structure. It would be something like an AlexNet or GoogleNet or ResNet or something like that, right? So what we can do is kind of like starting as like, we start one of these more, well-defined models and then try to tweak it. Another thing that can be done is some sort of, search space model. There are lots of works to show that, you can do a space search in order to find a model that is more relevant. Another thing that can happen is there could be the two-step attack where the first step, what happens is basically the attacker tries to infer the structure first. So for example, when we're talking about things like side channels, we'll talk about that. So for example, if the attacker somehow can get access to the server, at least the internals of the server, they can do some sort of, get this knowledge about, so from this layer to this layer, here's the inputs and outputs and so on and so forth. Right, so these are usually the kind of things that are being done, but of course this is not a completely solved challenge. So it's an open problem still. All right.
Okay, thank you.
Does this make sense? Yeah.
Sure.
Yeah, and somebody in the chat says the note that the goal of the shadow model is not to have the exact architecture encoding of the target, but to mimic the, yeah, exactly. So as I said, what we care about is we want to mimic the black box model of that. Probably the correct answer would be something very similar structurally to the actual original model, but doesn't mean that it has to be exactly right. So think about it as, we have an algorithm 1 and then we have an algorithm 2. And what we want to do is that algorithm 2 behaves very similarly to algorithm 1, right? Are they the same complexity or the same nature or not? We don't know. It could be, it could not, right? So. Of course, whatever we do in order to improve this accuracy, that's what matters in terms of the attack. Any other questions? So yeah, we said, so basically, I think we covered this already. So is it a white box or is it a black box? Do we know the structure or not? What is a query model? How many times can we query this original model? What sort of information are we getting from the model? Is it just, the labels? Is it confidence value, all the confidence values, some of the confidence values, so on and so forth? And again, what sort of network are we trying to mimic? Does it have just linear layers? Does it have nonlinear layers? How deep it is, and so on and so forth. So all these questions really change how we can extract the model. All right, so I mean, hopefully we have like 1 or 2 presentations this week and next week, so we can talk a little bit more about model extraction as well. So now let's move on to the second attacks, which called membership inference, right? So what is the goal of the membership inference? The goal of the membership inference is basically having a data record and the black box access to the model. We want to determine that whether the specific record was used in the training data set or not. So essentially what we want to do is that, let's say we have different, candidates or input records, right? And what we want to do is that telling that whether, for example, this candidate has been used during this training or this one has been used or not. So for example, out of 4, we can say, oh, this one has been used or these 3 hasn't been used. Why would that be useful? So there are multiple different scenarios that this can be used. For example, the fact that somebody has participated in the training data set or not by itself could be very, very useful in some cases. Another thing could be that basically by understanding which records has been used during the training set and which record has not, we can kind of like start from a core and then augment this in order to replicate the data sets, similar data sets that being used for the actual training, right? So these are different use cases for the membership inference. In all cases, what we are trying to do is violating the privacy of the participants and the individual records in the membership inference attacks, all right? Any specific question here? So how does the membership inference work? So basically the membership inference is like this. So we have the black box access to the model. This is the original model that sits in the cloud. And of course we have some sort of like a prediction APIs and the training API. So this data set is the one that we are trying to attack. So during the training phase and using the training API, this data will be used to train this model. So we are done with this part. And now we are at the prediction API, the prediction phase. So what will happen is that, let's say we have 2 possible set of inputs that we can send. So we can send some sort of inputs that are actually from this data set here. And then we can also send another set of inputs that are not part of the training data set, right? So any possible input that we send during the inference are either coming from the training data set or not coming from the data set. And what happens is that we're going to get 2 set of answers, right? A classification for those that are within the data set, and then a classification from those that are not from the data set. And what we want to do is that we want to distinguish the difference between this one and this one. So if we can actually manage to answer this question, that is this inference labels or this classification refers to a to the input record that is actually part of the data set or not, basically we can do the membership inference attacks. Basically, for any new X that we are sending to our model, we get some sort of classification, right? If we can answer whether this was part of the this was coming from an input that was part of the training data set or not, we can basically say that whether this X was part of the data set or not. And what we do is that eventually we are saying basically we are violating the privacy of this X, which refers to some participants during the training. All right, so hopefully that was clear enough. Any questions here? Arjun?
So is the purpose of this attack to like re-infer the training data set?
Yeah, in some sense, yes. We want to first of all answer this binary question that whether this X belongs to the original data set that we use for training this network or not. So we want to answer this question. And by answering this question, we basically can infer lots of important information. First of all, this might be relevant to a specific person. So we know that whether that person existed in that training set or not. Another thing that we can use is that now that we have this ability to detect which one is coming from the data training set and which one is not coming from the training set, then we can actually try to replicate this data set with some shadow data sets called the prime. And this way we can now use it, for example, for other things. So the membership inference could be the seed for another attack in the system. All right.
Thank you.
Yep. Question in the chat, how can you ensure that you have a relatively equal number of samples to input from the training versus non-training as an attacker? So that's actually a challenge. So finding those inputs is a challenge, but we're going to talk a little bit about the data sets generation and so on. And so I mean, yes, of course, if you don't have any information about at least the distribution of the data set or that specific records, that's the problem. But the idea here is that we have a larger data set, right? So let's call it D double prime, which part of it is actually D and the rest of it is D prime. And this D is part of the data set and this D prime is not part of the data set. So for creating the attack, the attacker draws, records from this larger data set. And what he wants to do is basically distinguish this from this, right? So that's what the membership inference is trying to do. Hopefully that's clear. Any other questions?
I have a question.
Go ahead.
Will there be a unique answer to this question? Can there be scenarios where the distributions of like training and non-training data be overlapping and we might not be able to arrive at a concrete answer or something?
Yeah, it could be definitely possible. There could be false positive scenarios as well. There could be scenarios where it would be difficult to find this. But what we are saying here is that there is a possibility for some specific data sets, there's a possibility to launch this. Yes. We're not saying or claiming that it's possible for every single model, every single data set. What we're showing here is that there's a possibility of this attacks for a specific group of data sets. Okay. So how does the attack work? So basically the systematic framework for the attack would be this. There will be a record X through the APR goes to this original model that sits in the cloud. So this is the original model. The original model is going to give us some sort of classification. So let's say, for example, a list of confidence values. It could be normalized, it could not, we may not be normalized, and so on. And what happens is that we want to create this model, which is basically this membership inference model or this attack model, which what it does is basically given this set of classification labels and this confidence values, create this binary decision yes or no, which yes means that this X belongs to the data set D. So yes means this, and no means that X does not belong to the data set. So that's the more formalized definition of the membership inference. Any questions here? All right, so how do we do that? So essentially what we need really is some sort of trained label, like labeled training data for this model that we want to train. So of course we need the confidence values and we need labels. So we need some sort of records that actually do belong to the original data set. And then we need some records that does not belong to the original data set. And not only that, we need the labels for them as well. So we actually know the ground truths for those labels as well, right? So this way, then we can have like a normal data set, D prime or D double prime or whatever you want to call it, or let's call it D attack, actually DA. And then this DA would goes through a regular machine learning training as many other systems as well. The complexity and the structure of this network could be also it's an open question, like what is the best structure for this? But usually people have shown that, not very deep, but relatively deep network with multiple layers, and probably some sort of like a convolutional neural net would be something that can be used for this attack model, right? So that would be the idea. So usually the way it works is that, as I said, there would be a larger data set. Part of it would be, I mean, the idea here is that, of course, we may not have access to original data set, but what we can do is kind of like mimic that behavior. So what we're going to do is that we're going to create a data set, which may not be exactly similar to the original data set, but at least maybe some sort of, distribution is the same, some statistics are the same, and so on. What we're going to do is then we're going to divide this larger data set into two pieces, 1 and 2. We're going to train the first one, the part number 1, to train our shadow model. The shadow model is basically a model that looks very similar to the original model. So it's kind of like some sort of like a model extraction in some cases, in some sense. So now we have our shadow model trained here. What we're going to do now is, this can even, we may not need to even do model extraction. We can just use the original API of the original system to do that, right? So basically, this is more of like, model extraction attacks at this point. Now that we have the shadow model trained, we extracted the model in some way. Now what we can do is basically now use this trained model and then feed it with the two groups of data that we have. And then this way we know the ground truths as well. We have the labels, and we have the confidence values, and we have the labels. Now we use this in order to train this one. So there will be another phase for training, and this is for training the attack model. And then we get the the yes and no. And now it comes to the actual attack time. Now we have this trained, and now what we want to do is actually getting the original values that we want. Right? So this would be the actual attack. So we use synthetic data to train our attack model. Now it's a time for actually using this attack model for the actual attack. So we basically create some records. We have some records that we want to make sure these are coming from the original data set or not. We use it through this attack model, and hopefully the attack model can give us the membership probability. All right, so this is like kind of like a two-step strategy. We start with some sort of synthetic data. We do some sort of like a shadow model, which like, subset of, model extraction. Then we use that in order to train our attack model. Then now we have the attack model ready. We put it here. We have the records the original records that were in question. We get the classification from the original model. We feed this classification into the attack model, and that's where the actual membership inference attacks is happening. All right. Any questions? So that's the idea of the membership inference. Membership inference, in some sense, reuse some notion of model extraction in it as well. And the goal, as I said, is actually recovering and violating the privacy of the participant. So at the very least, what we are revealing is that whether a specific participant has participated during the training or not, right? All right, so the third and final, privacy attacks is usually what's called a model inversion or reconstruction attack. So the idea here is given that we have some sort of access to the model, we want to actually reconstruct some sort of, record of the training. So we can either recover the entire record, or we can maybe infer some attributes about that. Before that, let's see, there's a question in the chat. So for the output of the attack model, is membership probability the percentage chance that the input is in the training data set or not? Yes, exactly. So if X was used during the original training, and if we use it for our membership inference attack, if the membership inference attack is accurate enough, that would be a high percentage, let's say like 95% or 90%, something like that percentage. That would be if this is actually part of the original training set. If it's not, then probably this would be a very small number. All right, so that's the idea of model membership inference. Okay, so back to the model inversion. So what the model inversion wants to do is actually recovering part of the training record. All right, could be an individual record, it could be a group of records, and so on and so forth. So how does generally this being used? So this is usually use some sort of like a generative network. So the idea is that we don't have the original image, but what we have is some sort of what is called an auxiliary knowledge, right? So this auxiliary knowledge could be partial data, could be collection of data that is kind of relevant or not. And in this case, what we want to do is that recovering the original image. So usually for model inversion, we already have some sort of information, but that information is not complete, and we want to get a complete information. All right. So what we do is basically use this auxiliary knowledge to create this generative network, and this generative network hopefully can eventually give us the image that we want. And how do we do that? We basically go through the normal generative training systems. We need to have, again, some ground truth. And using that ground truth, we managed to label the systems, improve the systems, and hopefully at some points this system would be accurate enough in order to recreate the data that we want. All right. So some sort of like similar to the way that we create shadow models, here we also have some sort of information and auxiliary knowledge and some label data. We use that to create this generative networks, and then we have some sort of feedback to tell how well this has been generated. Back and forth iteration as a normal generative model, the way it works, we can eventually get to the point that we can now have the original image. All right. And then once we do the training, of course, during the attack phase, again, we will have some sort of partial knowledge. We're gonna feed it into our GAN. And then what will happen is that we're going to get the original record that we want, right? And again, as I said, we don't necessarily need to recover the entire, for example, image. Let's say, for example, we have some auxiliary knowledge and we want to get, for example, the gender, right? So we want to infer the gender of these auxiliary knowledge. So that could be also another possibility. So it doesn't necessarily have to be the entire image or entire record, but could be some sensitive attributes of that record. Right? So somebody asked, does that mean model inversion and membership inference are all meant to obtain information about training data? Exactly. As I said, we basically, if the user is the attacker, the user is interested in two types of information. One is the information about the model itself, which would be the weight and structure, which goes into the category of the model extraction. Or the user, the attacker, is interested in training data. So either the presence of a specific record in the training data or some sensitive attributes of that training data, which would be the membership inference attacks and the model inversion attack. All right. Any other questions? So your voice is so faint. Can you speak a little bit louder?
Hear me now?
Yeah, a little bit better.
Yeah. I was just going to ask, like the previous example that you showed, recovering the image base. Is this referred to for the model that would be used to make like a base?
I'm sorry, but I cannot really. Can you put it in the chat? I guess it's easier that way.
Yes, I will.
Yeah, sorry. All right, so let's, in the meantime, let's see, there's another question in the chat. What are the target labels? And what is the difference between pair loss and identity loss? So, I mean, this is a specific example for a specific paper. What we are trying to do here, it's not, oh yeah, prior loss. So what we are trying to do here is kind of like, we are trying to train this generative network. And what we want to do is basically saying that, given some ground truth, we want to see how accurate the inputs that we create, the samples that we have created it is, right? We can have many different metrics. So this, just as I said, a specific example, but generally the general idea is that we want to be able to create this generator, which give us that given some auxiliary knowledge, this could be, again, in the specific example, could be mask or blurred images and so on. Given the specific, auxiliary knowledge can give us the accurate record of that inputs. If it's just a general picture, that would be the metric that we would define would be different than if you want to do some sort of like a gender classification. All right. Okay, so let me see questions. All right, so the one question is already answered. Isn't membership inference a subset of model inversion? Not really. So membership inference trying to just tell the presence. Model inversion is like in some case a much more difficult question. And they're kind of like trying to address two different things. One is the presence and the other one is the actual record, right? So the way that we approach these two problems are kind of different, but they are relevant, obviously. Can one possible defense mechanism against model inversion attacks be learning the gradients of the inversion model in order to mimic the adversary? This may be used to compute the noise vector in order to turn the output into an adversarial example for maximizing the reconstruction error. So maybe you want to elaborate a little bit on this, but do you mean like, the defense mechanism intentionally creating some sort of errors in order to kind of like fool the generative model? Is that what you're meaning, or is it something else?
Yeah, essentially, I mean like learning the noise vector and computing the noise vector which mimics the adversary in order to maximize the reconstruction error of the inversion model itself, so as to provide a defense mechanism for the attack.
So, and then if we learn that model, if we learn that distribution, what will happen next? What would be our strategy in order to improve the defense?
Then we can maybe use that as labels to train the model.
Oh, you mean some sort of like adversarial training?
Yes.
Yeah, definitely. You can do that in order to yes, probably okay. That could be one possible solution. Yes.
Thanks.
Sorry about the noise. All right, so similar to the other attacks, again, the main challenge in model inversion is what sort of auxiliary information is available. That's the key thing in model inversion, that what we do have and how we can train our generative model, right? Another thing is what sort of information do we have about the original network? Is it a white box, black box, so on and so forth? And then the attack model, obviously, here is what are we trying to reconstruct and recover? Are we trying to recover the entire record, some set of attributes, so on and so forth? Again, what is available from the original model side and so on? That these are all specific questions that we need to answer in order to do the model inversion. And among the three, the model inversion is the most challenging one, really, specifically if you want to try to actually recover the entire record. So that's one thing that to keep in mind. All right. And again, as I said, what needs to be reconstructed is another challenge. Entire record, some set of a feature. Of course, if you go down, like if we need less information to be reconstructed, the chances that we have a successful attack is much more high, right? All right, so defense mechanism against all of these. So there is a range of different. Kiara, you have a question?
Yeah, Professor. So with these sort of attacks, and they only can access to the train data, the data that used for training. They cannot access the other users' data that, for example, they just using their network for getting outputs.
Sure. I mean, if it depends, right? If that sort of input is also being used for maybe updating the network, then possibly you can get information about them as well. But if, for example, let's say that you have a model that has lists of different data for the inference, since this data does not change the behavior of the model in any short form or shape, then yeah, of course, there's no information to be reconstructed from, right? So the reason that we can recover the training is that information is already embedded inside this model, and that's why we can recover it. If the information is not embedded, then you cannot recover.
Okay, thank you.
Does it make sense? Questions? All right, so defenses, a range of solutions. So one of the main ways of doing this is adding some sort of noise to the response. Think about it. So for both, model extraction and membership inference, for example, since we kind of query the original network, and then we get some sort of like a classification values. If we add some sort of like a small noise to the classification values that we get from the systems, then people have shown that this makes very difficult for example, doing a successful model extraction or membership inference. All right. So because the classification labels are not exactly the same as what it's supposed to be, it makes the training of these much more noisier and much more difficult. All right. So of course, there will be a utility versus privacy problem. When you're adding this noise, you're not only making this prediction harder, but you're also making the original prediction harder as well. Remember that we are using machine learning as a service to actually label our data, right? So if you're adding noise, we are also hurt. The normal users will be hurt too, right? So this should be, added in a very smart and systematic way. It's not just, we add noise. Of course, if we make the, output labels as a random distribution, then the possibility of, having a successful membership or model extraction attacks would be almost zero, right? But on the other hand, the usefulness and utility of the systems would be also equal to zero. Imagine a system that's, the labels would be completely random, right? This would be completely useless. So there's this, utility versus privacy, and you will see a lot when we were talking about privacy preserving, privacy in general for machine learning. We are seeing, lots of these utility versus privacy issues, unfortunately. And then this is kind of going back to one of those security principles that there will be overhead when you're doing, when you're adding some security or privacy, features to your systems. For example, in this case, the overhead would be the decrease in accuracy, right? Another thing that can be done is that protecting the model and data set itself. So how does that, how we can do that? Remember, we said that basically querying the model is something that usually most of these attacks need. So maybe we can do some sort of, ways of like, if there is a malicious, set of, queries, or if somebody tries to like very regularly query the model with some specific pattern, maybe we can detect that. So that could be another way to kind of like, eliminate the entire attack from the beginning. Retraining the model in some sense that, we do some sort of like an adversarial training, as one of the students was mentioning. This could be, again, another possible solutions for this. Kind of like this 2 and 4 kind of relevant to each other. So one could be like, limiting the amount of queries. The other one could be, for example, if you see specific patterns in the queries of users. Another thing that we can do is some sort of authentication before actually giving access to the users, right? So for example, say, okay, this is like an open, access system, but for now you need to first also like tell us exactly who you are, who wants to access this, and so on and so forth. So some sort of authentication can also happen. And there are many more solutions. Some of them are actually also relevant to things that we discussed during the security model. So, overfittings and regularization, things like that. There could be some correlation between them and how easy it would be to, for example, do membership inference or not. So for example, for the membership inference, overfitting is one of the key challenges. So if you can reduce overfitting, then we probably can improve our robustness against membership inference and so on. All right. So again, range of defenses, we're not going to go through the details, but hopefully if you read more papers, you will learn more about it. All right. Any questions at this point? Grace?
Could you elaborate on the retraining the model bit? I don't quite understand that.
So the retraining means like same way that we were saying that, for example, if you want to reduce the overfitting, right? Not just retraining, it's doing exactly the same. I think it's slightly misleading, this term. I should have changed it. But I'm thinking, but what I'm saying is that knowing the problem that you have and doing things like adversarial training or any sort of other mechanism that you can use in order to reduce, for example, overfitting. Does it make sense?
Okay, thank you.
Somebody say a query didn't get adding noise to the response. So what we're saying is basically this. So you see that what we, for example, do in membership inference is that we query the original model and we get this classifications, all right? So what we're suggesting is that when we are giving the classifications, we do the classifications and add some noise to it. This way, the attack model will get noisy inputs. And people have shown that this noisy inputs could result in an incorrect membership inference probability and so on. So that would be the idea. Is a differential privacy mechanism to add noise to the output? Yes. So when we want to do add noise, we can do something like differential privacy. It could be other ways of doing adding noise. We still haven't talked about differential privacy, but when we get to that point, we will maybe come back and talk about it as well. As a countermeasure to previous examples where noise was added to the adversary effect results. Wait, the countermeasure to previous examples where noise was added to. Bashir, can you maybe elaborate your question? I don't fully understand it, sorry. Justin, you have a question?
Yeah, so for the defenses such as detecting adversary query patterns and monitoring queries for users, would the adversary behavior possibly affect the normal use case of a general user? Like, could there be like a denial of service, or will general users still be able to use the model?
It could be a denial of service, but think about this, that since this is like usually machine learning services are paid system. So like for every single query, you have to pay some money. Generally, denial of service would be very expensive and usually not possible because the bandwidth at which, the ML system actually gets and accepts, queries is already limited. But of course, denial of service is always an issue in any sort of server-based system. So somebody can keep, sending queries such that the other users cannot use it. Yes.
Thank you.
Hi, Professor. It looks like there is some conversation going on in the text chat, but I'll say what I was referring to was like in the previous lecture where we had like an image of a duck and then noise was added to it. And then it made the system think it was a picture of a horse or something like this. I was wondering if like what you were talking about or what one thing you could do was using noise as a defense for that.
For this type of privacy attacks or for those original security attacks? I didn't get that.
Like could we use noise as a defense to using noise to generate an adversarial output is what I'm asking. Oh,
so you want to intentionally create an incorrect label, and what you're suggesting is that adding noise to the input so that we intentionally create that incorrect output. Is that what you're suggesting?
I need to figure out how to describe this. Like if someone plans to make an attack that uses noise to generate an adversarial output, could you in turn come up with a system that uses noise to counteract that?
Yeah, so that's the whole idea of like things like adversarial training, right? So we kind of discussed it last time. Yes. One of the ways of protecting the system is doing the training with this in mind that, okay, there will be, so let's intentionally add noise, retrain the system. And then now the decision boundaries is hopefully more robust to this change. So that's the main idea is what's called adversarial training, basically. So perfect. We intentionally add noise during the training to make that. What we're suggesting here by adding noise, we are adding noise to the labels, right? So the inference happens normally. We get the labels that we want, confidence values. When we are sending it to the outside world, we are adding some sort of noise to it. And since this outputs will be used to train some sort of attack model, what's going to happen is that the model that's going to be trained based off these noisy inputs will make a wrong decision. So basically, this way we kind of like using the idea of adversarial neural networks in order to force the attack model to make a wrong decision. All right, so let me see what is in the chat if I need to answer anything. Okay, I guess it's okay. All right, any other questions? Okay, so we already burned lots of time. So let's a little bit talk about the paper presentation. So if you follow my post in CampusWire, you should probably see there's a table that I published that shows you the time and the paper that you need to present. So please make sure that you fully understand that. Contact your teammates. Usually there is one teammate for every, so there's 2 people for presentation. Contact them, and what you need to do, probably CampusWire could be a good way of contacting those people. DM them and find them. Let me know if there is an issue. So for example, you cannot reach out to your teammate, or teammate is dropping the course or is not planning to present or something like that. So any sort of issue that is happening for your teammates, it's your responsibility to let me know. I think the paper assignments is okay. So there are people who still haven't filled the form. You will have until the Friday this week to fill it. What I'm going to do is that I'm going to have another pass sometime over the weekend and assign a new set of papers for those people who haven't filled it in. So still there is some openings that you can do. If you don't do it by Friday, I'm assuming that you are either planning to drop this course, you want to just audit this course, or you're fine with getting B or lower, because that would be, I think the presentation would be 30% of your grade, all right? So, and then as I said before, if you're just planning to audit the course, there's no problem. You can stay on CampusWire, you can watch the lectures and so on. So if you're planning to drop it as soon as possible, right? So any questions about the paper presentations? Any issues or anything that somebody wants to say? So, and then the first paper presentation going to be on this Wednesday, all right? So those people who are presenting this Wednesday, I understand this is like a short notice. Sorry about that, but this is, we cannot do anything else. So I already missed the first week. We couldn't miss this week. So, and then on the other hand, we have to wait for all the people to fill in the form. So sorry, but you will get some bonus point because of that, all right? So paper reviews. So again, those 4 papers that we're going to present on Wednesday, you have to review it by Wednesday as well. One thing to help those people who are presenting their paper, you can submit your reviews until Friday. All right. So only for those 8 people who are presenting, it's okay to submit your reviews later. Most of the class have to submit their reviews by Wednesday before the class. And the reason is that you have to read the paper so that you can actually understand what the presentation is about. Again, it will be short notice. From next week, you will have the entire full week for doing that. And then for the project, we create a document for people to share their ideas, what they want to do. One quick update that since there are many of you and maybe not all of you will be able to do a project, I'm giving this option, another option for the project, and that would be some sort of like a final exam, all right? So instead of doing a project, you can just do a take-home exam on the Friday of last week, week 10. I'm gonna post this on CampusWire just to make it clear. But if you don't want to do any of the projects that I mentioned, you can take the final exam option. So that's also another possibility. All right, any questions? There is no template for the presentation, but in lecture 1, I already discussed what I'm expecting for the presentation. What you should do, what's the first slide, what's the second slide, how many slides it should be, and so on. All right, so are there prior exam papers? No, there are no prior exam papers, but what I'm gonna do is probably giving you some sort of like sample of like, these are the questions. As I said again, in the first lecture, the quiz and the exam would be more of like an open-ended questions, like, oh, we have this problem, what are the possible solutions and so on. More of a design problems, not like, mathematical problems, right? Okay, so let's take a 5-minute break and then we're gonna come back and talk about other things, right? Okay. So far we said that, what will happen if the user is the adversary. We talked about different type of attacks that the user can do. Stealing the model waste, training data, some sort of record of the training data. So now let's look at, what will happen if the server cannot be trusted, all right? So in this scenario, which is like actually very common, generally, this would be a default scenario for any sort of like, edge and cloud settings. So there will be an edge device. There will be some data collected maybe by some sensors or some files and so on. And then there will be the server, right? And then the edge, in order to do the cloud computing. So for example, let's say the edge device does not have the computational resources, or does not have the capabilities, or does not have the actual access to the actual model. But in that case, the edge has to offload the data to this server. Machine learning as a service is one of those examples. So what will happen in that case is that the server will see the data, the raw data, and see it in clear, right? So if the edge device does not have trust in the server, then essentially this model cannot happen. So the offloading cannot happen. What can be happen instead? Of course, one thing that can happen instead is that the edge device do the computation locally, right? So everything happens locally. Nothing really leaves the device. Nothing leaves the edge device. But that has lots of problems, right? So we need to come up and think about some ideas that how we can leverage the cloud computing platform and the resources available in the cloud without giving up the privacy in cases that the privacy is important, all right? So the answer to this, okay, what can we do? Interestingly, this is not a new problem. It's an old problem. Of course, it's getting more and more important these days, mainly because of machine learning as the main motivator, and because of this, vast, creation of data, the billions and millions of records that we create every day. But this is not something that's, this is not a problem that's been created now. It's actually an old problem. And there are some actually old solutions to it as well. One of the very, very old problems about this, and one of the very famous problems about this, is what's called a millionaire's problem, all right? So the millionaire's problem, or sometimes called Yao's millionaire's problem, is this problem that, let's say two people, Alice and Bob, both of them are millionaires, and they are interested to know which one is richer, all right? But obviously the problem here is that none of them trust the other person, so they don't want to reveal their net worth. So what they want to do is that finding a way without revealing the actual wealth, then they want to know which one is richer. So of course, maybe you think that this is not intuitive. They have to without actually sharing this information. Probably it's not, there is no possible solution, but very interestingly, there is actually a couple of solutions for this problem, all right? So obviously the trivial solution for this is either one of them announce the net worth and the other person say yes or no, or both of them announce their net worth, and then they know that whether it's going to be, which one is higher. The other solution could be some sort of like a third party, right? Where there's some sort of an aggregator or mediator that both Alice and Bob trust. They both tell that person that this is my, net worth. The other person also say that, and that person announce who has the bigger net worth, right? But again, the problem here is that there is no third party. There is no central trust. So the only thing that happens is that there are two users. They want to know who has the most. They don't trust each other. They don't trust anybody else as well. So under these circumstances, we want to solve this problem, right? Any questions so far? Okay. So let's see how I actually fix this issue. And so this is actually a quite interesting solution. So what happens is that, let's say Bob, so let's say there's Alice and Bob, and let's say for now, the values that Bob's can get is only 4 possible values, right? So let's say Bob can get either 10, 20, 30, or 40 million. And this is just to simplify the assumptions. So what Bob can do is basically Bob gonna go and buy 4 boxes, all right? It's gonna label them 4, 3, 2, and 1, right? And then Bob gonna also buy 4 locks. Bob's gonna also buy 4 locks for these 4 boxes. So I'm going to give you an intuitive solution. Obviously, I'm not giving you a mathematical solution, but we're going to actually go to that mathematical solution soon as well. And then these 4 boxes that Bob is buying, only one of them actually has a key. All right. So only one of them has a key, and that's the key that Bob's has. All right. So Bob's only has key to one of these 4. All right. So what Bob can do is that basically based of his input, he can basically label this. So for example, let's say Bob has key to this box here. So, and let's say Bob has like $40 million. What Bob's can do is that say that, okay, this is 3, maybe this is 4, this is 2, and this is 1. They just change the labels, right? So basically, Bob has only key to this 40 million, and that's all Bob has, right? And then this basically 1 key out of this 4. Then what Bob can do is basically sending all of these 4 boxes to Alice. One thing to note is that these boxes looks exactly the same. So Alice does not know which one is which, basically. It just sees the labels, but these are looking exactly similar. Another thing that Alice does not know is that which key Bob has access to, all right? Again, these are very similar, boxes, similar to each other. So the only thing that Alice knows is that this is box number 1, this is box number 2, this is box number 3, and this is box number 4, all right? So now what Alice does is that based on her input, so let's say Alice, for example, has $30 million. What she's gonna do is sending some sort of yes or no's into these boxes. And then the way that she's gonna do it is obviously her income, is her net worth is bigger than the value inside in each of these boxes. She's gonna put yes, and then if her net worth is less, she's gonna put no. So for example, since she has 3 million, she's gonna put yes inside this, yes inside this, and maybe no and no inside here, right? So only if it's greater than those labels. So she's gonna treat this as 10 million, she's gonna treat this 20, 30, and 40, right? So she's gonna just, in her private, just gonna send this inside these boxes. So Bob will not see what sort of answer she has provided to this. She's gonna just, Alice gonna just agrees that she put correct labels, correct answers to each of these boxes. Then what Alice gonna do is that send back these boxes to Bob, and Bob now sees again 4 boxes. And now the key is that Bob only has key to 1. Bob has key to this number 3. So he's gonna go and open this box and he's gonna see no, which means that Alice's net worth is less than Bob's net worth. So he's gonna show this no, and that will be the answer to the question that whether Alice has more net worth than Bob. All right. And then if you can see here, none of them actually knows exactly what is the net worth of the other, right? The only thing that Alice is seeing is 4 boxes with 4 labels. She does not have any idea what is inside those boxes. She does not have any idea which key Bob has. And on the other hand, Bob only has access to one of these boxes, right? So if he managed to open all those boxes, of course, he can see that, for example, these two are yeses and these two are nos. So he can quickly figure out what is the Alice net worth is. But the only thing that Bob sees is that the answer to his question, which is basically the 30 million. All right. So that's the answer to this question. So somebody asked, what if Alice lies? And that's a great question. So generally the millionaire problem here, what they try to do is that they're trying to get the answer for a question that both of them have. So in this case, both Alice and Bob's will willingly participate in this protocol. So we call them honest but curious, which means that they are curious about the answer of the other person, about the data of the other person, but both of them are honest in following the protocol. All right. So what they're trying to do is that since both of them needs to get the answer of this question. So both of them are interested in getting the answer to this question. Both of them willingly and correctly participate in this protocol. All right. So in that case, that's why Alice puts the correct, labels inside this. That's why Bob only has key to one of these things, and so on and so forth. So both of them follow exactly the protocol because both of them wants to know exactly how much money the other person has. Right. So that's the reason that this works. Of course, there are actual cryptographic methods to make sure that this protocol that's like very intuitively I described actually happens exactly as this. We're not going to go through it, but this is the idea that we are doing. All right. So let's see, there are a bunch of questions. So let's see. So I already answered the question of what if Alice lies. So somebody says, well, she put yes or no inside each box, so she knows exactly what is in each box. Yes, she knows the labels, but she doesn't know which one is for the Bob. So which one Bob has the key to, right? So that's the key part. That Alice, of course, knows the boxes, but does not know whether Bob has key to box number 1, 2, or 3, or 4. Like how Bob has labeled this is the information that Alice doesn't have, right? So are the wealth inside box chosen by Bob so that his wealth falls between the biggest and smallest box bet? Yeah, so I simplified the example. I'm saying that let's say this is a discrete problem. So there's only 4 possible answers to this question. That's why we started with 4 boxes, all right? If it's a continuous problem, there are solutions for it, which we're not going to talk about. But let's say that it's only the wealth could be one of these 4 numbers. That's the assumption that we have when we're solving this problem. And later on, we're going to show why this is a correct assumption. Okay. In this scenario, she exactly knows that Bob has 4 million just for this example. Oh yes, for this, I mean, since there are 4 different possibilities, of course, but let's say that the number of possibilities are many, right? And so in that case, they don't know exactly the answer. Okay. Does Bob's box thing is exact or is it like a lower bound or something? As I said, we're giving this example saying that these are the exact wealth of all of them, right? Doesn't Bob learn that less than 4 million? Yes, that's the question. So somebody says, doesn't Bob learn that Alice has less than 4 million? So that's the answer that they want to know, right? So they want to know who has the bigger value. Of course, this is the information that both of them are willing to make it public, right? So if at the end of this, interaction, somebody says that Alice has more money than Bob, of course, Bob will know that, Alice has more money than 30 million that he has, right? So that's the answer that both of them are okay to know. What they don't want is the exact number, right? Yeah, so somebody already answered my answer. He doesn't know how much less she has. I guess Alice knows that Bob exact wealth is 1. Yeah, guys, I mean, this way of chatting makes the class really, really slow, right? So you have to actually, if you want to have a discussion, make it online so everybody can watch. I cannot read like 11 messages here, all right? So somebody raise a hand. I'm not going to follow more chats. So if anybody has any pressing question, just raise your hand and I'll answer. Okay. Vishnu?
Doesn't Alice know more about Bob? Because now Alice knows what are the like in the discrete scenario. She knows whatever values, like she knows what values are present, and she knows where she put yes and no. So she most probably knows the range of what the wealth of Bob is, right?
No, so she only has this binary information that whether Bob has more money than hers or not. That's the only information that Alice is gonna get, right? So let's say that there's hundreds of these boxes, right? So at some point she's gonna just put yes below it and no's above it, right? And then the only thing that Bob's gonna reveal is just yes, just one answer that this is yes or no, right? So the only thing that Alice will learn is that Bob has more or less money than hers. And this is a public information that both of them are willing to provide. Does it make sense?
Yeah, got it.
Yeah. Caleb?
Oh, I just wanted to go off of that last question. I think that what he was saying is that in addition to knowing whether Alice has more or less money than Bob, she also has a set of discrete values out of those however many boxes there are. And I know you said that there are a lot of boxes, but like I guess even if there are 100 boxes, his value or like the or I guess her value, yes or no, could be relatively close to one of the ends if you order them. So like maybe there are only 2 boxes greater than her wealth, and you know that he has greater wealth than her, so he has either one of those 2, I guess.
Yeah, that's, I mean, again, that's not a problem, right? So she already know that if the answer to the question is no, she has less or more wealth. And that's not the problem. Again, the only thing that these two care about is that which one has more information without knowing the absolute value. So for example, even if it's the only 2 possibilities, there's a 50% chance of there's one or the other, right? So that's, I mean, you're talking about the corner case in the specific scenario. But again, if there is a limited amount of choices and we want to do the comparison for that limited amount, of course we are revealing some information about let's say these 2. So that's not an issue. That's not the problem with the protocol. It's just because there is finite states, and knowing that if you're bigger than some states, you get more information. That's not an issue. Roy or Rui, let me know which. Can you pronounce your name first?
It's actually just call me Ray, okay?
Ray, okay.
Yeah, so my problem is that I just want to make sure that the idea behind this solution is that instead of using a third party, which is either insecure or inconvenient in reality, I don't know, they pass on a kind of a message or talking between them and update this message so that they can know each other's the comparison between their wealth instead of the actual number of their wealth, right?
Exactly. So I mean, this is because of lack of that third-party trust. Of course, if there were a third-party trust, what they could have done is that both Alice and Bob would have tell that third party what their wealth is, and that third party do the simple comparison and then announce the results. The reason that we go through this hassle is because there is no third party, or there is a third party, but none of them actually trust that third party. Does that make sense?
Yeah, thank you.
Yeah, and this is actually a very valid scenario. So think about all these, cloud computing scenarios. So let's say we don't trust Amazon Web Services or Google, but we want to do some computation. What we can do is then using methods like this. So we're actually going to talk about that. Kiarash.
So just for clarification, with this method, only Bob can know whether Alice's welfare is more or less than him. if Alice wants to know about Bob's, and she must to do it herself, she must provide box.
Correct. So the way it works is that Bob will announce the final results. So Bob will have to show the answer to Alice as well. Again, as I said, this is a part of the protocol, and both of them has to follow that protocol. So the way it works is that, yeah, the Bob will announce. Basically, Bob will show this piece of paper that Alice put. So that would be the guarantee that the answer is correct.
I see. Yeah.
That's it. Okay. So yeah, somebody says that this is basically called secure multi-party computation. Yes, this is called. I mean, we're gonna get to that part. Yes, this is multi-party computation in some sense. Yes. Any other questions? All right. So this is one example of a bigger picture. That's what we call privacy-preserving computation. All right. So then that's what we want to talk about today, and we are talking about today, and then hopefully next lecture. So basically, this is the idea in privacy-preserving computation is there's methods for evaluating a specific function where inputs are provided by two or more players, all right? And the problem here is that they mutually distrust each other, so they don't trust each other, and there is no central third party, all right? So there is no central third party, so the whole cloud computing, criteria is obsolete. And then they don't trust each other as well, so they cannot just announce their results, all right? And then function could be any function. So for example, what we just described was, greater than or equal or less than or something. But you can easily, expand this to any other functions, as we will show more formally during this lecture and next lecture. Right? So this is the issue of the privacy computation. What are the solutions? The solution that I just described is part of what is called a multi-party computations. This is specifically the one that I described to you was two-party computation because there were two parties. Some people call it secure multi-party. Some people just call it multi-party computation, but they're interchangeable. There are other solutions for this as we're going to describe in this lecture and next lecture. The famous one is what's called homomorphic encryption, which I'm going to just describe in a minute. There's also other methods, including secret sharing and then differential privacy. These are also very interesting. We're going to talk about it next lecture. And then there's also methods that is purely hardware-based. So basically, it's not an algorithm, but the way that the hardware can give us the trust. So we don't trust entities, but we trust hardware. And then hardware can give us some applications and functionality for us to do that. So we're going to actually talk a lot about this when we're talking about trusted execution environments. The part that doesn't matter who controls that hardware, it's always trusted. Yes, somebody said, is it then Intel SGX? Intel SGX is one of the examples of this, correct? And then finally, there are some non-cryptographic methods, including things like federated learning or split learning and adversarial representation learnings and so on. We're going to talk about a little bit about those as well, right? Garbled secrets is actually a secure multi-party computation. It's not part of trusted execution environments. Just answering the chat. All right. So now let's talk about all of these one by one. I already a little bit talked about multi-party computation. I'm going to go back and talk a little bit more in a more formal settings. But let's start with actually the encryption and homomorphic encryption, right? So you might ask this question that why don't we just encrypt data and then do computation, right? So can basically encryption help? And the answer to that is that encryption does not help with the computation. Why? Because encryption is mainly used for communication and for storage. So encryption, as we will talk more extensively next week about different, encryption methods and so on, is only used when you're storing some data in some database, you can encrypt it and store it, or when you're doing the communication between, for example, Alice and Bob. This communication can be secure. But for example, if Alice wants to, add two numbers, A and B, if these two numbers are coming from Bob, it has to be first decrypted and then added, and that's why we can only do computation. In other words, we cannot do computation over encryption, all right? So that's why encryption cannot help. But the question is, what if we can do computation over encryption? So basically, the idea is that we have, let's say, two inputs, M1 and M2. What we do is that we encrypt M1, we do get C1 ciphertext 1 and ciphertext 2. And let's say, for example, the function that we want to do is a simple addition. So what we want to do, we wanted to get the value of M2 plus M1, let's call it Y. This is ideally what we want to have. So let me say, what if there exists an encryption mechanism that if I added C1 and C2, and then maybe get C3, and if I decrypt this, I get Y. So this would be exactly what we're looking for, right? Because in that case, what will happen is that this would be our edge. So forget about this part, we don't have this part. So this would be our edge. The edge is gonna encrypt the data, create C1 and C2. What is gonna happen is that the edge is gonna send this to the cloud. So that would be our cloud. The cloud gonna do this summation for us, gonna send us back C3. We're gonna decrypt C3. We're gonna decrypt C3. So this goes to decryption. And we're gonna get our Y, which is equal to M1 plus M2, right? So the additions, which in this case, I mean, of course, it's not a significant activity, but in some cases, let's say we can substitute this addition with something like a machine learning inference, right? So let's say we want to do the inference on specific data sample. What we can do is that we encrypt it, send the encrypted data to the cloud. The cloud apply the machine learning into the encrypted data. It gets this C3 value, which is the encrypted output of this. The cloud has no idea what this value is, has no idea what this value is, because both of them are encrypted, and by definition means that they cannot find the original text. Well, what happens is that this data will be sent back to the edge device. The only thing that the edge device needs to do is decrypt this data, which is very simple, and then gets the final value that it wants, right? And it's as if that this data has been gone through normal machine learning inference, and the data, the output label is created, right? So this is what homomorphic encryption will try to achieve, and we're going to talk about how. Any questions here? So I already talked about this. So more formally, what we want to do is we want to apply any sort of, function that we want. We have an input X, and we want to apply this function and get Y, right? So what happens is that instead of doing this, instead of sending this X to the cloud and do this in the cloud, what we are doing is that we are encrypting this X and send C. We send C to the cloud, and then do F, and then we get, Y prime. We do the decryption and get Y, right? So that's what the homomorphic encryption will tell us. Hopefully, if the homomorphic encryption, so basically what the homomorphic encryption does is this part here, that it does this, apply this F on an encrypted data instead of the normal data, right? Any questions? All right, so just to give you a little bit, background information about the homomorphic encryption. So homomorphic encryption is basically just similar crypto systems that AES and RSA and others. They're basically regular, crypto system that has all those functionalities. As I said, next week we're going to talk a little bit more about encryption and decryption and generally cryptography. So there you're going to know a little bit about AES and RSA. So whatever we talk there can be applied to homomorphic encryption as well. The added functionality in homomorphic encryption is that you can do computation over encryption. You cannot do that on AES. You cannot do that on RSA. You cannot do that in any other cryptographic mechanism. So that's the biggest advantage of homomorphic encryption. Homomorphic encryption itself is not a new problem. It's been an old problem. It's actually starting in the 80s, and people thought about what would happen if we have something like this. But what happened was like in 2009 is actually a time there was a breakthrough in homomorphic encryption. People have actually found much more efficient algorithms and new algorithm called bootstrapping, which actually enables fully homomorphic encryption. We're going to talk about it later. And then homomorphic encryption, again, similar to other encryption mechanism, can be symmetric or asymmetric. Again, next week, we're going to talk about what these are, all right? So just let's actually, before actually going through how it works, let's see what are the goals. So in homomorphic encryption, specifically in HE, the goal is evaluating polynomial functions, all right? So specifically HE is targeting polynomial functions. We're gonna talk about what will happen for non-polynomial functions, but for now, just know that what we need to do is evaluating polynomial functions. And since we only need polynomial, it means that basically what we need to do is being able to support addition and multiplication. So if there is two ciphertexts, and then the added value of this, if we decrypt this, and this would be, let's say xy, this would be equal to xy. This is just satisfying the addition test. And then same for multiplication. So if you do 2 and it's equal to xy, the results of decryption of this is similar to this. Basically, we have a homomorphic encryption crypto system. It has to be able to add two ciphertexts, has to be able to multiply two ciphertexts, all right? So that's all a homomorphic encryption needs to do, all right? So that is the goal that we are looking at. So we are looking at an encryption mechanism that if you add two ciphertexts, or if you multiply two ciphertexts, is as if that you are adding the original data together, or multiplying two original data, right? Any questions so far? All right, so let's start with a very silly example. So let's say we have 3 and 7. So let's say we want to, multiply and add this. So this is our M1 is 3 and our M2 is 7. So let's say that our homomorphic encryption mechanism is just multiplying by 2, right? So our encryption mechanism is that whatever the input is, I'm just multiplying it by 2, right? So what happens in this case, that would be 6. And for 7, it would be 14. So now if I add them together, it would be 20. And the decryption would be then basically dividing it by 2. So if I divide this by 2, that would be 10. And if you look at the addition, basically if I had added 3 and 7, I would have get 10 too. So basically this method of encryption that is basically just saying whatever x is, my encryption is 2x, is homomorphic under addition, right? So that's how we define homomorphic encryption for addition. So let's see how about the multiplication. So let's do the silly example again. So this would be 6. This would be 14. And if I multiply this together, that would be 84, right? So if I divide this by 2 times 2, because basically multiplying is kind of like, you do both of them together, you get 21, which is again similar to 3 times 7. So it's kind of like again, our silly example, for the multiplication, we need to also kind of do this hacking of, like, depending on how many times that we are doing, we need to repeat the decryption multiple times. So that's the only hacking that we need to do. Kiarash?
With these methods, it can crack the encryption. For example, if the algorithm finds the 0 in multiplication, it can detect the 0, and with the 0, it can, with summation, it can detect all of the numbers. So it can, crack the encryption.
Yeah, that's whatever. Hence it's a silly example, right? So it's not a secure example. It's just an example that's showing that, it's possible to do homomorphic encryption.
No,
does it make sense?
I'm not talking about exactly times 2. I'm talking about whatever algorithm you have in. So if if you can do kind of multiplication after the encryption, so You know, I think you
No,
can
but
track
what if
the.
if I map 0 to 1, 1, 1, 1, and then 1 to maybe 1, 0, 1, 0. And then in that case, if I multiply this.
So for sure, for the multiplying of this must be 0, exactly. Oh, so, I getting right now. So the encryption and decryption can be different. I
Yeah,
thought
it could be different. Yeah, it could be different. It could be mapped to any other value. So it could be completely different labels. So it doesn't have to be. I mean, we will show about the security of this. Don't worry about it. But yes, I mean, this is a valid observation. Sure.
Okay, thank you.
Yep. So is the decryption method known by the cloud computer? So yes, the decryption is known, but decryption usually use some sort of key, right? So for example, in this case, decryption is just division, right? So the decryption algorithm is division. The key in this case is 2. So the assumption is that the cloud does not know what the key is. And that's where it cannot decrypt, right? But again, this is not a secure example. It's just a silly example. But basically, encryption in this case is multiplying, decryption is division, and the secret key is 2, right? So maybe another time the key would be 4, and actually you can test this. If you change 2 to 4, you will see that still this method works, right? So again, division, multiplication, secret key would be 4 in both cases, and it works, right? So again, when we are talking about encryption, we will talk about encryption and decryption algorithms. And since I said the security should not be by obscurity, we will say that, you know, the algorithms for encryption and detection are known. The only thing that is not known is the key, the secret key. So we will talk about how the secret key will use that. So again, in this case, multiplication and division are the algorithms. The secret key is that value that we're going to divide by or multiply by, which is 2, right? The system has to be linear, exactly. So when we are talking about polynomial, we are talking about linear systems, right? But again, for this examples, yes, the system has to be linear. Are these examples symmetric? I'm not sure about what do you mean by symmetric, but oh, you mean symmetric keys? Yes, in this case, it's a symmetric key. Okay, so far the only thing that I was trying to show you is that with some encryption mechanisms, although very silly, it's possible to achieve what we want to achieve. And what we want to achieve is that we want to add these two numbers or multiply these two numbers, and we're going to get these answers. But we don't want to directly do this addition. We want to do some sort of encryption, which in this case is just a simple multiplication, do the actual addition or do the actual multiplication on the cloud, and then do some sort of decryption and get the final answer. And then if the answer is similar to this, then we are happy with our encryption mechanism, right? But of course, the biggest challenge is the security of this. So the attacker should not be able to infer the results. So that's the whole point. And that's why we need to improve this mechanism, because obviously after seeing a bunch of different pair of inputs and outputs, the attacker can easily figure out that the encryption is just multiplication by 2. So this is by no means a secure encryption mechanism. So this is not something that we want to do in real systems. All right. So let's see how we are going to improve this. So let's actually make it a little bit more complicated. And we're going to later on show that why we are making this decision. So let's say again that we have message 1 and message 2. These are the two messages that we want to do the addition and multiplication. And now let's this time say that we have some sort of a random vector S. And this S, in addition to this S, we also have two matrices C1 and C2. And the way that we create this matrices is that this matrices C1 and C2 has the eigenvector of S. So basically S, the eigenvector of C1 and C2. And M1 and M2 are the eigenvalues of these matrices. If you don't remember what eigenvector and eigenvalues are, you can just quickly, probably after this class, Google it. This is just a simple, linear algebra, but generally, the way that we create, C times sum S is equal to MS. We usually call this eigenvalues, and we call this eigenvector. So this is a vector, this is the matrix, and this is just a value, all right? And this is a vector. And there are standard ways of finding these values, so we can easily do that and create this, all right? So let's see how this actually would be useful. So our crypto systems actually, if you, again, go back to linear algebra, you will see that if you add these two matrices together, just element-wise, the eigenvalue of this would be eigenvalue of their individual matrices. So if for this one is M1 and for this one is M2, if you add them together and get C3, the eigenvalue of C3 would be M1 plus M2. Right? And another interesting thing that you will see is that, again, if the eigenvalue of C1 is M1 and C2 is M2, if you multiply this using standard matrix multiplication algorithms, you will see that for C3, the eigenvalue would be M1 times M2. And how this would be useful? Basically, you can easily see this, how this would be useful, right? So basically, we're going to get a crypto system where our plain text would be M1 and M2. Our ciphertext would be our C1 and C2, those two matrices. And our key would be basically S, all right? So the key would be S in both cases. So same for both of them. And the homomorphism comes from this fact that if I add C1 and C2, or if I multiply C1 and C2, and if I find the eigenvalue of C3, which is the addition, the product of this, that would be as if I'm adding M1 plus to M2 or M1 times M2, all right? So the homomorphism coming from this fact. And the decryption is also quite easy. So given S and M, there are methods for, if I have M1 and S, there are easy methods for creating C1, standard linear algebra methods. And again, given C1 and S, there are methods for finding the eigenvalue. So this would be our encryption mechanism, and this would be our decryption mechanism, which given
Professor, you're frozen.
all right, guys, sorry about that. So I don't know what happened to. All right. Okay. Can you hear me? Yes. Okay. All right. So so we were saying that so I guess this is where my kind of voice was went out, was going out. So the encryption and decryption mechanism would be that basically for encryption given M and S, there are standards, linear algebra methodologies for creating C. So we basically, all we need is creating C. So that would be our encryption mechanism. And for decryption given C and S, we can decrypt and get M1. All right, so that would be the decryption mechanism. What's this? Sorry about that. So this would be, our encryption and decryption in this homomorphic encryption mechanism. Is there any questions? Sorry, there was some confusion, so probably there will be some questions. Any questions? Seems we're good to go. So of course, the question is this secure? And unfortunately, the answer to this is that of course not. Given C, it's very easy to find the eigenvectors and eigenvalues. All right, so there are, again, standard mechanisms for you can just brute force and search, and you can easily find eigenvectors and eigenvalues in very short time. So that's the problem with this. So what we want to have is that the adversary sees C's, but given that the adversary does not have access to S, in no ways the adversary can find what M is. But what, unfortunately, this eigenvector and eigenvalue will give us is that given C, there are ways for searching through for finding the eigenvectors and eigenvalues in small time. And then eventually the attacker will find M, and that's the problem, right? So this is not secure, but of course it's encouraging, right? It's slightly better than our silly example, but we are almost there. So what should we do now? The answer to that is that we're going to talk about the next lecture, but to just give you a short overview, we're going to use something called an approximate eigenvectors. So the idea is basically what we want to do is using this very known problem called learning with errors. And with learning with errors, what we're going to do is we're going to create not CS equal to MS, but we're going to create this CS equal to MS plus some E. And there is actually, proven ways that shows that this way, the system, you cannot easily find this S or this M. So you cannot easily find this M if you don't have S. So there are proven methods for it, which we're going to talk about, that relies into this thing called learning with errors. And hopefully once we show that, you will understand how this works, and we get our homomorphic encryption mechanism that we want. All right. So yeah, here's where we're going to stop. Is there any questions? Okay, so just a quick reminder, don't forget about paper reviews due by Wednesday, 2 p.m. Don't forget about the presentations, those 8 people that have to present this week. Please prepare your slides. As I said before, 2 options you have, either do record it and send the recording and they're going to play the recording during the class, or just do the live lecture, which is the preferred method. All right, so that's it for today. Thank you, everybody. Okay, somebody has a question. So in the silly example, how does the cloud figure out we multiply by 2? And basically by just saying iterative, multiple of instances, and then they can figure out what the method is. Next week we're going to talk a little bit about security of crypto systems and the type of attacks that can happen in a crypto system. So there you can see a more systematic way of reverse engineering the encryption and so on. Okay, thank you, everybody.